Over the past 10 years, I've really changed my engine building. The introduction of non-breakable apex seals, moving from ceramic to more of an exotic steel E&J seal, has allowed me to push the envelope when it comes to the boost and nitrous. I've also started using aluminum blocks, which are allowing us to have stronger blocks that cool better. And we're also moving into higher octane ethanols, which are a cooler burning fuel, which has less carbon buildup, allowing us to push even more boost and run even longer durations of time because everything's running cooler. My original favorite apex seal would have been the ceramic apex seal, ran by Mazda in the 787B, the 4 rotors in Le Mans. This is a very good quality apex seal that will sustain heat, sustain boost, sustain nitrous, and last an extremely long time as long as you don't detonate. Another new addition to our program is lightweight rotors. For a long time, CNC cutting rotors has been very expensive and only for elite builds. With Built to Apex, Mazda Tricks, and other companies now offering CNC Lightning, you're getting the ability to cut more weight out of rotors. So this particular rotor, we shaved about 1/3 of a pound out of it, allowing us to run even higher RPMs and higher boost in our race cars. We originally started with a cast iron side plate using OEM tension bolts. As machining rotary motors got better and better, we started using studs in those OEM plates. This allowed for a strengthening of the block, and we started to go to oversized studs using steel, titanium, creating lighter, stronger motors. We came to the realization we couldn't add enough studs to truly strengthen these blocks the way we wanted to. We also wanted lighter weight blocks. With our plates flipped over, another big improvement is additional cooling surface area. You can see the billet ink actually has a removable faceplate, creating a modular plate design. So in the advent of a blow up or needing to resurface your side housing, with your modern rotary, you can actually remove that faceplate and put a fully new one in there. The improved cooling passages, improved stud placement and sizing all lead to a stronger, better cooling block. As I raced in Formula D and built different motors, we experimented with different porting. We went from a street port to a bridge port all the way to a peripheral port. Each one of these changing our port timing, which would be a lot like changing cam timing. As we went more aggressive, the horsepower got peakier and easier to make. Yeah, we generated those high numbers. Bigger seemed better, but we were killing our bottom end. So we realized we needed that broad power band. And we actually brought our porting all the way back down to a street port that we designed ourselves. And that gave us the ability with high octane fuel, high boost numbers, to use a basic street port to get a very broad power band to fight against those bigger displacement motors with our small displacement rotary motors. Your OEM steel apex seals. Great for daily driving, mild boost, can easily go 100,000 miles, but they are susceptible to breakage under detonation. Here we've got Mazda ceramic apex seals. These are derivative from the Mazda 787B 4-rotor Le Mans car. Under extreme conditions, high RPMs, high boost, these seals will last forever. Unfortunately, being ceramic, any detonation causes them to break, and you're talking about a lot of shrapnel going through your motor. Here we've got our modern steel seal. This would be an aftermarket apex seal done by E&J. There's a lot of brands out there. But the biggest attribute to these is they don't break under detonation. Here I've actually got a seal that suffered mild detonation and it is bent. It can't be run, it's no good, but you don't have debris going through the motor, so you're not likely to hurt your turbo, rotor housings, or other components, allowing you to push the envelope in your rotary motors. The downside is, being a softer material, they just don't last as long as your OEM or ceramic seals. So it doesn't matter whether I'm talking about my Formula Drift car or other performance rotary engines, I often get asked what is going to be the most common component failure. And I think even if you look on the internet, apex seals truly take the rap. In my opinion though, it's not the apex seal's fault. Apex seals spontaneously don't combust. They don't just jump off a bridge, crack, or blow up. It's kind of like a piston ring. They're just the part, the component in the engine that if anything else isn't operating right, they're the first component to get damaged. Your apex seal is going to get damaged if your fuel delivery isn't right, if your octane isn't right, if your air temperature on your intake is not correct. if your ignition system isn't working right. So it's not the apex seal that's jumping off the bridge, it's something else in the car that's not functioning right that's leading to an apex seal failure. So I want everybody to think next time they have a piston ring or an apex seal fail, take a look at that car, figure out what other part of your system is not functioning right. All right, Kyle Mohan here, and we're talking about rotaries. Here we've got our 1.3 liter 13B eccentric shaft. If you're taking that 13B rotor and multiplying its face compression, 654 cc's times 2, you're going to get approximately 1.3 liters or 1,308 cc's. Depending on the level of the build, that 2-rotor 13B can generate anywhere from 200 to 500 horsepower, and even more depending on the turbocharging. Here, moving on to the Mazda 20B, approximately 2 liters, taking that same multiplication of 654 cc's now times 3, you're coming up actually slightly under 2 liters with 1,962 cc's. It doesn't matter. Whether it's naturally aspirated or turbocharged, you can easily generate anywhere from 250 to 500 horsepower, with your extreme race builds easily generating over 1,000 horsepower with your 3-rotor motor. Here you've got your 4-rotor shaft. The 4 rotors taking that same 654 cc rotor and just using it 4 times. So that multiplication gives you approximately 2,622 cc's, so it's actually slightly over 2.6 liters. In Mazda's race trim, it did 700 horsepower naturally aspirated in the Le Mans cars. I've seen these motors in turbocharged trim well over 1,000 horsepower reliably, with your average builds being anywhere from 350 to 700 horsepower. Gotta love the rotary. With a small package, you're still able to generate high horsepower. Last year at SEMA, Kyle Mohan Racing debuted this amazing twin turbocharged ethanol burning FD3S. But ever since then, I've been getting asked, Kyle, what are you gonna do with this amazing build? Well, that's what I wanna know. Should we take it, try to set a record in an airstrip attack event? Should I turn it into my next Formula Drift car? Maybe I just need to do some really big smoky burnouts or go road racing again. There's a lot of options. I'd love to hear what everybody thinks I should do with this beautiful FD3S RX-7. We decided to go with a lightweight flywheel. And if you notice, it's actually a smaller disc size. So we've moved our weight more towards the center, so that's going to help our rotating speed. If you look at the disc itself, it's a metallic disc with springs, so we're going to have a good amount of friction area locking up. This should be able to hold a fair amount of horsepower, but we've also got these springs in there, so via the pedal for the driver, it still should be a nice streetable, usable clutch. With our friction surfaces wiped off, we're now going to put the first disc down. Make sure you're not touching the actual friction surfaces. You don't want to get any fingerprints or oil or residue on there. Nice and clean. Here's our first floating disc that's going in. This is the other running surface for the twin disc setup. Same thing, we want to wipe it off with acetone or some type of non-residue leaving cleaner. All right, we're getting ready to install our clutch setup. So we've got the engine on our Mazda Trix engine stand, and we're using that flywheel stop to hold it in place. We've got this nice Exity double disc setup going on here. I've already got the flywheel installed, and I've already got my pilot bearing with fresh grease and a fresh bearing and seal installed. All right, on this rebuild, we reused our existing eccentric shaft, so it's still got a used pilot bearing and seal in there, and I'm going to use my Mazda factory pilot bearing seal removal tool to pop those out. If you're using a new eccentric shaft in your rebuild, it should come with a new seal and bearing, but you definitely want to check this and always make sure you've got some good grease down there on the bearing. A couple taps of the slide hammer should pop it out. There you go. All right, on this rebuild, we reused our existing eccentric shaft, so it's still got a used pilot bearing and seal in there, and I'm going to use my Mazda factory pilot bearing seal removal tool to pop those out. If you're using a new eccentric shaft in your rebuild, it should come with a new seal and bearing, but you definitely want to check this and always make sure you've got some good grease down there on the bearing. A couple taps of the slide hammer should pop it out. There you go. All right, so we're getting our motor squared up in the engine bay so we can lower it down in and clamp the motor and transmission together. Once we've got the motor and transmission bolted together, we'll then be able to lower them down together into those motor mount pockets. As we're lowering our motor down in, we want to be careful to not hit the back of the clutch on the input shaft. With this build, we're pretty fortunate. All of our turbos, our exhaust, our power steering, ABS is all out of the car right now, and some of it's being deleted. So depending on the level of the build or how close to OEM you are, there may be components that are still in your way. Some of those components are gonna be in your way. Take your time, use bungee cords, do what you need to strap things to the chassis or frame rails so it makes it easier to lower your motor down in. Anytime you're looking at the back of the motor and you have your pilot bearing and seal removed, it's a good idea to check the bore of the hole. You wouldn't want any debris, damage, anything like that going on in there. That could compromise your next bearing and seal. When I'm dealing with motors, I like stuff to be clean. So I've already wiped out the hole where the pilot bearing and seal was, and I'm just gonna do a little final wipe off with a little acetone to remove the last little bit of grease, debris, anything that might compromise our existing new seal. And same thing with our flywheel needing to be tightened down to a specific torque spec onto this counterweight. I wouldn't want any dirt, paint, dust on there either. I've got my new factory pilot bearing and the Mazda Tricks installation tool. We're gonna keep our bearing and seal separate so we don't beat up our seal while we're installing it, but we're simply gonna tap that with a hammer down into our eccentric shaft. When you're looking at your pressure plate, the fingers of the diaphragm right in here are what are actually generating the force that you feel in your leg or the clamp force that's pushing on the disc. So you can easily look at a pressure plate and tell whether it's a very aggressive setup or something that might be a little more drivable. This looks to be a nice good in-between setup. It'll handle a lot of horsepower, but shouldn't break your leg. For installation, we're just dropping it down in, aligning our blue marks. The blue line is actually indicating the balance of your flywheel from the factory to the clutch setup. Installing our second disc down onto that first floater plate. Now that we've got our second disc on here, we've actually got two different splines we need to line up, so Exedy provides a little alignment tool. We want to make sure we get that down in there and get both discs aligned. Final wipe off on our last floating disc. We're going to drop that on, line up the blue line, make sure everything's still nice and lined up. All right, we're still keeping the motor centered. We're not hitting anything. We're going to start to move the motor inward a little bit. Just watching out for the back of that clutch on the input shaft. And we'll start to lower it down a little more. And we're just gauging distance between our oil pan area and our flywheel, clutch to back of transmission area. Slowly working our way down in. Just to keep everything lined up, I need to bring the transmission up a little more. As we're lowering the motor down in, we just want to make sure not to hit that pressure plate, that ring that's back here, on the input shaft. That could cause it to not properly engage on the throwout bearing. We now have our input shaft lined up, and the flywheel is actually inside the bell housing. With our motor and transmission snugged up together, we can now lower our floor jack out from underneath the transmission and start to lower the whole motor and transmission down into our motor mount pockets. Floor jack's out of the way. Now our whole motor and transmission is suspended. All right, I'm going to lower the motor down into those pockets, and then we can adjust our motor mounts to drop into their actual holes. There we go. There we go. With a little bit of a pry, obviously being careful, we can get those motor mounts to just drop down into those pockets. Within your 2mm 13B Apex seal lineup, there's variations in materials, corner piece design, spring layouts, but if you really look at it, all of the manufacturers really had the same goal in mind. If it's a 2-piece or even a 3-piece design, you're looking at long-term sealing the ability for the seal to slide around and move within the motor is just a great seal. And the one-piece design, it's just manufactured for strength. The leading edges, the weights, the materials all serve different goals and different purposes. So it's a matter of doing research and deciding what seal is going to best suit your motor, and also looking at what people have been able to accomplish with those seals in the past. In the world of apex seals right now, the two-piece apex seal seems to be the most popular. The one piece residing more on the racing side, and with Mazda's discontinuation of the three-piece, it's a little hard to get. A lot of engine builders on the street and performance side still consider the three-piece design one of the best sealing apex seals, with companies like Yamamiya in Japan and other manufacturers around the world still taking two-piece seals and sending them out to actually be EDM cut into a three-piece. On my side, I believe the two-piece is very adequate. Mazda has continued to make the two-piece seals both for the RX-8 and 13B applications, and I've seen them easily go over 100,000 miles in average street use. On my race cars and on the racing side, I tend to lean towards two-piece and one-piece. I'm Kyle Mohan. We're going to talk a little bit about rotary engine break-in. So if you've put together a brand new motor, or you've received a brand new motor from a shop, or even the manufacturer, there's obviously some break-in procedure necessary. Like most new components, your Mazda engine will need to have about 500 miles put on it. Nice, low load, low RPM driving conditions. That means no burnouts, no flooring it, no passing cars on the freeway unnecessarily. Get that first 500 miles on it as smooth as possible, gradually increasing that mild load to the point where you can change that oil and actually put another 1,500 miles on it. So your first two oil changes should be done by the time you hit 2,000 miles. By the time you've hit 2,000 miles, you should have accomplished a proper rotary engine break-in. At that point, you're free to have fun. But there still are times when you need a one-piece apex seal. I get asked quite often, can I build somebody a full Bridgeport motor? Meaning both side housings have bridges. Once you've gone to a full bridge, you can't have a corner piece anymore. So here's a really bad example. You can see right here on this Bridgeport template that if you had the corner piece in the spot where the bridge was, that corner piece is going to fall in your bridge hole, which you think about it, that's not going to do anything to help your apex seal out. It literally could fall in there and break, or if it does run, the wear would be so extreme, it wouldn't last very long at all. So if you're thinking full bridge, you also got to think one piece. I like running singles on my race car. It's just easier to make a lot of power. This twin setup behind me, it looks real cool, but there's twice as much plumbing, twice as much work going into it. It's going to make a lot of power. It's going to be awesome, and it looks amazing. But I could have done the same power with a single turbo. And when you're utilizing fuels, RPM, porting, different tuning ECUs, the days of being stuck with a lot of lag when the 93 to 95 RX-7 was built have started to pass. Your modern turbo and your modern ECU is capable of a lot faster spool up than the turbo and computer technology was when those cars were first put on the market. Continuing with our idea that we wanted to pay homage to the original FD3S, which was an amazing twin-turbo 13B track monster, only we didn't want to go with stock twin turbos, and nobody really made an aftermarket twin turbo setup that was large enough or to our likings for this build. So we decided to build a thick wall stainless steel manifold in-house. You can see we've got twin Turbonetics Evolution gates. I've done a little porting on the inlets here. We've welded both the exterior and inside where we could. So we've got a nice strong manifold that's going to hold two good-sized Turbonetics turbos. All right, Kyle Mohan Racing. We're hanging out with drifting.com in front of our beautiful FD3S project. And we're trying to listen to the audience. So everybody said they'd love to see a Formula D FD3S, and we're kind of still deciding. So if anybody out there has an FD3S chassis that might work for one of our projects in the future, let us know. It could become one of our next projects. So right here, I've got one of the oil coolers, not a radiator, but actually one of the oil coolers off of my Formula D car. And I actually run 2 of these with about 3-gallon capacity of oil. Your 13B and 3 rotor are capable of generating as much heat as a racing V8 motor. They're operating at 100% duty cycle in a very, very compact space. That's part of the magic and how they make so much power. The car behind me right here, you can see it actually has twin oil coolers with a V-mount setup being put inside. We're trying to get as much fresh air to as many necessary cooling components as we can. On your rotary cars, never undersize your fans, never undersize your radiators, and never undersize your oil coolers. The rotors are actually oil cooled, so you're relying on that oil to help cool the motor just as much as you are the water. We decided to go with a lightweight flywheel setup and clutch setup, so we chose an Exedy Hyper Twin. For installation, we just want to line up our holes to our counterweight. Exedy created this cool little character to help you with the bolt pattern sequence, in case you're wondering. Going to use the nice Exedy supplied bolts. They've got a nice flat surface, nice big head. Clamp everything down nice. I like to start them by hand to avoid any cross-threading. When torquing down your flywheel, make sure to use OE or the clutch manufacturer's specs. They do vary depending on the bolt and the clutch setup, so always use the manufacturer as a reference. Before we go any further and we start cleaning off our actual friction surfaces, I want to grease my new pilot bearing. You always want to make sure you get some grease in there. Use a nice high quality grease. Make sure you don't have any excess. We'll wipe that off with a rag. But if that bearing fails, you're not going to be able to get the car in or out of gear while you're driving. Final wipe off on our last floating disc. I'm going to drop that on, line up the blue line. Make sure everything's still nice and lined up. And the last step, pressure plates going on. Make sure our hardware lines up and our balance line, that blue line right there, indicating that everything's still matching our factory balance. All right, so we're getting ready to tighten up our pressure plate. We've got our alignment tool in, everything's been cleaned. And this is where that little cartoon character from Exedy really comes into play. So when we left off with our KMR Project FD3S, we had just dropped the motor into the chassis. We were getting ready to do most of our bench assembly with our turbos. We assembled our turbo, manifold, and wastegate setup on the bench, installing all the gaskets and most of the fittings, so that way we could put the whole setup on as one big chunk. Whether you're dealing with an OEM turbo setup or an aftermarket setup, it's good to do some test fitting. If you can install the motor with your all turbo setup on it, that's actually a very easy way to do it. In our case, we didn't have that flexibility, so we chose to install the turbo, wastegates, and manifolding as a chunk after the motor got put in. I'm Kyle Mohan. I've been building rotary motors for many years, and I also run a 1,000 horsepower plus 3-rotor in my Mazda MX-5 and Formula Drift. And I get asked questions about apex seals all the time. What are they made out of? Do they break? What should I run? Is thicker better? Is thinner better? Well, we're going to answer some questions and delve into it just a little bit. Those ones are supposed to be unbreakable. For my engine builds and my personal race cars, I needed an apex seal that was going to have the versatility of handling high horsepower, high abuse, and also still had good longevity. With testing and the help of my good friends and partners over at E&J, we're actually getting ready to debut a new KMR tested apex seal, same as what we're running in my Formula D car. I'm Kyle Mohan, I build rotary engines. What causes low compression? We're going to talk about some of the most popular causes. Everybody blames the apex seal, and yeah, the apex seal is a likely component. It can break, it can get stuck, it can be damaged by debris getting sucked into the motor if you don't have proper filtration. You can also damage your side seals, you can damage your corner seals by over revving or not having proper lubrication. A lot of the times you can even stick seals if there's too much carbon buildup, Or if you're starting to lose a bearing, don't have proper oiling, over rev, too cold of a startup with not the proper lubrication, wow, there's actually a lot of causes of low compression. Another thing to consider is the temperature of your motor. If your motor's running hot, overheating, the rotary motor is a very small motor that has to make a lot of power. So it's got to do something with that heat. That heat is absorbed by both your water cooling system and your oil cooling system. Kyle Mohan Racing here, and we're still deciding what to do with our FD3S. So if anybody else out there has a FD3S chassis that might work for a KMR project, let us know. We're always searching for good, bad ideas like this one. So this is a pretty unique body kit we got for this particular project. It's actually imported from Japan and a BN Sports new design. So we wanted to ask some questions. People were wondering what it was. If anybody's interested, this is literally a bolt-on kit. It's custom, but it's custom from Japan. So check it out. BN Sports Mastermind, Kyle Mohan Racing. This is the Kyle Mohan Racing 6-port half-bridge template. So this would be used on your 86 through 91 Mazda RX-7, which is one of the most popular motors in the United States and the easiest one to come by. If you're not looking to street port, if you're looking to get a little bit more sound, a little bit more horsepower, stretch the legs of that rotary motor, this is a great porting option. You're not really sacrificing reliability, and you're definitely increasing airflow. Half-bridge, 6-port porting template, KMR. Kyle Mohan Racing, drifting.com, rotary, engine building, restoration, and knowledge about what your internal rotary motor looks like and what it means. We've got two housings sitting here. One, obviously showing some signs of wear, some signs of use. One looking a lot cleaner and a lot fresher. Whether you're rebuilding, building a race motor, or just restoring potentially a classic rotary engine, when you take it apart, there's some easy identification marks to let you know whether the housing can be used or should be resurfaced or is not usable at all. At a quick glance, this particular housing could look fairly usable. The first things that I look for would be the water jacket area. This internal O-ring is the most important barrier. That's your main head gasket seal between your combustion area and your actual water cooling side. You also want to check your outer O-ring seal to make sure there's no heavy corrosion, missing pieces of cast iron, or anything that might compromise your actual sealing area. Although the water jacket area does look intact and very clean at this point, one of the first things I notice is the discoloration between the area that the water's passing through and where the actual rotor housing and actual tension bolt is landing. This can be a sign of some warpage, that you're not getting equal pressure throughout the rotor housing and side housing. Whether this is a new or used housing, this would lead me to believe that this probably needs some resurfacing. Even though there's not any heavy corrosion, we're probably going to find some low and high spots on this motor. A second thing that I'm noticing right here is this is the rotor pattern, and it looks like the rotor sat in a fixed position for a long time. There's always been a lot of concerns regarding around resurfacing of rotary components. But one thing I always remind people is this is a very normal process in engine building throughout the world. If you're rebuilding any typical piston motor, you would not rebuild it without decking the heads, honing the piston walls. It would not be considered a rebuild. So for me, one of the biggest things that I notice in rotary building is a lot of people will put this component back in and call it a rebuild. I would not call it a rebuild. I would call it a put back together of used components. When we are actually resurfaced, we've checked the housings, we're bringing it back to a state of OEM tolerance and fresh material. Now you've actually got something that's going to hold compression. You're not going to have any leakage or oil smoke on startup due to the hash marks or wear marks that the oil control rings make. But people are often concerned you're taking off that first layer. You always want to look out for motors that have been sitting for long periods of time. Rotaries or any piston motor, if it's a cast iron or aluminum block, are sustainable to corrosion, rust, erosion. So if something's been sitting for a long time, and even though it was good or it was claimed to have been good, you want to really make sure that it's going to turn over freely and not have any bind spots. Also, if there's any water that's been enclosed in that block sitting internally, that could lead to internal rust buildup. So if you're buying a JDM block or something that's been sitting for a long time, I view that more as a core. I know I'm going to take it apart. I'm going to see what I get usable out of it. If you're looking for good usable parts, you want something that's got compression, that hasn't been blown up and doesn't have any obvious signs of overheating. Motors that have been overheated, blown up, are often going to have internal damage. A quick visual explanation. Here would be the port shape and size for your street port. Here would be your peripheral port, where we're going straight through the rotor housing. You're changing your port timing and your size. Thinking bigger obviously is better, this would be the equivalent to a very large cam in a piston motor. This would be your much more streetable cam. Running more boost in either, you're still going to have a very high peak power with this, broader power band with this. If I've got a block with a lot of corrosion on it, it doesn't mean it's instantly junk. You've got to clean it up, potentially lap down the side housings, spec everything back out, and find what can still be brought back into usable specs. There's obviously more work involved, so it really depends on what your goals are with the build. You can start with JDM motors, you can start with Mazda motors, you can start with US spec takeouts, or with brand new components. It's just a matter of what quality or what your end goals are. I've been able to take motors that were literally rusted and corroded, not even turning over from Japan, and bring them back into 1,000 horsepower 3 rotors. And I've seen people start with brand new components and have them last very shortly. So it's not just the components in the motor, it's also the time and effort you put in on top of it. All right, preparing our stainless steel hand TIG welded manifold for our final assembly. We've got our gaskets on, our studs installed. I recommend a little anti-seize. Anytime you're putting studs into stainless, it's more of a concern of them galling and sticking than them staying in there, in my concern. This thing's going to expand and shrink. So we've got to do a little final installation of our gasket, tighten down our wastegates, and then we can get this in the car. Finishing up our assembly of our exhaust manifold, I want to get this last dump tube on. We'll tighten it down and then do a test fit of our turbos, making sure nothing's hitting. When we actually do our assembly into the car, it'll be just the manifold, and then we'll put our intake manifold on and then the turbos. That's one of the reasons I have this whole assembly off while we did our motor installation, was everything's so tight, there's kind of an order to the installation on this car. Alongside our twin turbos, we've got this nice CX Racing lower intake manifold. It's got larger runners and 6 injector ports along that secondary rail, giving us a home for those 2000 cc injectors we got from Evolved Injection. We're going to be running ethanol in this setup, so we wanted to make sure we had ample air and fuel delivery so we could achieve our horsepower goals.